In the last episode, we explained how to use in-wheel motors to establish the 5 degree of freedom equations of the vehicle. In this episode, we explain another important innovation in the paper, the decoupling of each motion. Establish the 3 degree of freedom kinematic equations and add the control forces and moments to the equations. First, longitudinal motion equation. mx double dot equals fx plus fd. Here, Fx is the applied longitudinal control force, and Fd is the driver's driving force. Then, lateral motion equation. M times V times beta dot plus r. Here, V times beta dot plus r is the lateral acceleration, minus ms times hs times phi double dot. This term is the lateral acceleration caused by the roll motion, equals fyf plus fyr plus fy. Fy is the applied lateral control force. Fyf is the front axial lateral force, equals kf times delta minus lf times r over v minus beta. Similarly, fyr can be expressed as follows. If you want to know the derivation process, you can refer to the previous video. Next, yaw motion equation. izr dot minus izx phi double dot equals lf times fyf minus lr times fyr plus fmz. Here, mz is the yaw control moment. Iz and izx are the yaw moment of inertia and the yaw roll product of inertia respectively. Next, the roll motion equation. Ix times phi double dot minus ms times hs times v times beta dot plus r. Here, v times beta dot plus r is the lateral acceleration, minus izx times r dot equals minus kx times phi minus cx times phi dot plus mx. mx is the roll control moment. Kx, Cx are the roll stiffness and damping respectively. Finally, the pitch motion equation. Iy times theta double dot equals m times x double dot. Here, theta double dot is the pitch acceleration. Mx double dot represents total vehicle longitudinal force. Assume the distribution ratio of the longitudinal force on the front axle is P, as explained in last episode. The front downward vertical force is generated by forward longitudinal force. So, the equation goes to times P times LF times tangent theta F plus, this is front, and plus rear 1 minus P times LR times tangent theta minus H minus K theta times theta minus theta theta times theta dot plus My. My is the applied pitch control moment. K theta and theta theta are the pitch stiffness and damping ratio respectively. Above we have completed the kinematic equations. In those equations, we applied Fx, Fy, Mz, Mx, My as control force or moment. Next, we need to extract the factors affecting yaw and roll. Through Laplace Transform, organize them into something like yaw equals ns over ds. Here, n and d are the numerator and the denominator of the transfer function. Using the superposition principle, organize the efforts of delta, mz, and mx on yaw, respectively. Similarly, organize the same results for yaw and pitch. Let's look at the derived results. We write the form of the equation like this. Yaw equals ds. Numerator is n delta r. This term represents the effort of the steering angle on the yaw rate. Similarly, for the mz and mx, they are the efforts of yaw moment and the roll moment on yaw rate. You see, all the ds here are the same, because in the transfer function, the denominator represents the inherent characteristics of the system, such as natural frequency, damping ratio. I explained the derivation process in details in the previous EP file. You can go and check it. Then from the equation, it is very obvious to see that yaw and roll are coupled with each other. So, how to decouple? The author proposed a very meaningful idea. The author's approach is to forcefully eliminate the roll term that efforts yaw, and at the same time, change the applied mz to mz prime. Change the above term into the form of the term mz prime. Then let top and bottom two equations be equal and find mz prime, directly solving the equation. The delta term can be directly cancelled out. Mz denominator is mzr. Numerator is mxr. This way we have found the decoupled yaw control moment mz prime. Similarly, find the decoupled roll control moment mx prime. After completing the decoupling of yaw and roll motion, we can now convert the above control strategies into control inputs. First, the input matrix before decoupling. U1 equals fx, mx, my, mz transposed. After decoupling, it is u1 prime equals fx, mx prime, my, mz prime transposed. u1 prime equals w times u1. We only need to find the w. Then we can input u1 to automatically achieve decoupling. The matrix of w is also very simple. Combining the equations of mz prime, mx prime, just derived can solve for it. Here, I write it out directly. Everyone can derive it themselves. Note, here, G24 is the coefficient, and G42 is this coefficient. Okay, this episode continues the context of the previous episode, completing the decoupling of the vehicle's various degrees of freedom, mainly the yaw and roll motions. After these two episodes of contact, everyone needs to understand 2 points. In-wheel motors can achieve 5 degrees of freedom control of the vehicle. How these 5 degrees of freedom achieve the decoupling control strategy? If you have questions, you can leave a message in the comments below the video. See you next time.